Section 3.5 is about implicit differentiation. The idea here is that we want to be able to find slopes of tangent lines for curves that are not necessarily functions. So in sections 3.1 through 3.5, we were always working with functions. An equation like this is not a function. You can see it's just the graph of the unit circle. So, but what if I want to know the slope of the tangent line at the point root 2 over 2 comma root 2 over 2? We can guess that the slope is about -1, but how can we compute the slope? One thing that we could do is we could solve for y. If I were to solve for y, I would get two different functions. I would get y is equal to the square root of 1 minus x squared. That would give me the top half of the unit circle. And then I would also get y is equal to the negative square root of 1 minus x squared. That would give me the bottom half of the unit circle. Then I could proceed to take the derivative of this function and evaluate it at root 2 over 2. So that's one technique we could use to find the derivative and the slope. However, you can't always solve for y. Okay, that's not always possible. So we're going to look at the second technique called implicit differentiation, okay, which will allow us to find the derivative of y with respect to x of a curve that's not necessarily a function. So here are the steps for implicit differentiation. The first thing we're going to do is differentiate both sides of the equation with respect to x. The key thing that you have to remember is that if you're differentiating an expression with y, you have to remember that y is a function of x. So if I'm differentiating with respect to x, I need to use the chain rule. So in this case, we would get our outside function is the cubing function, and the inside function is y. So the derivative is 3y squared times the derivative of the inside function, which is y prime. The second step of implicit differentiation is that we solve for y prime. Okay, so I'm going to go back to the original example with the circle and show you how to use implicit differentiation to show, find the derivative and to show that the slope here is -1. So example 1, find the slope of the tangent line to the unit circle at this point. So step 1, I'm going to differentiate both sides with respect to x. Okay, so the derivative of x squared is just 2x. And here's where I have to be careful. The derivative of y squared with respect to x, not y, is 2y times, this is to the first power, by the way, times y prime. And then the derivative of 1 is just 0. Okay? So now what I'm going to do is I'm going to do the second step, and I'm going to solve for y prime. So 2x plus 2y y prime is equal to 0 implies 2y y prime is equal to -2x. So this is telling me that the derivative is given by -x over y, where xy is any point on the graph, where of course y can't be 0. So in the example at the top, if I want to know the slope at root 2 over 2 comma root 2 over 2, it's going to be equal to negative root 2 over 2 divided by root 2 over 2, which is just -1, as we predicted from the image. Here is one more example. Find y prime for the curve xy minus x to the 7th equal to 5y squared. So I'm going to do the steps once again. I'm going to differentiate with respect to x. Okay, and here I have to use the product rule. So I'm going to use the product rule here. So I have the derivative of x is 1. I multiply it by y plus x times the derivative of y is y prime. Now I'm going to take the derivative of x to the 7th. That's 7x to the 6th. This is 10y times y prime. And the second step is to solve for y prime. So I see it appears in this term, So I'm going to get the terms that contain y prime on one side of the equation. Okay, and then I'm going to factor them out. And divide. So this implies that y prime is given by y minus 7x to the 6th over 10y minus x. So given any point on the graph, I can actually find the derivative using this formula. Last example, basic example, we're going to find the derivative of y with respect to x for this curve. Again, this is not a function, and you would have a really hard time trying to solve for y. Okay, so let's start this. Step 1, I take the derivative of both sides. Let me just write it up here, because I don't want to rewrite this whole thing. Okay, and then I end up with negative sine of y plus 3 times y prime, so I'm using the chain rule, plus 5x to the 4th cosine of y squared times 2y times y prime. So I had to use the chain rule twice there. Plus 3e to the y times y prime. So this term, and this term all contain y prime. So I'm going to get them all on the same side of the equation. So that I can factor them out. And divide. Let me just write this a little more neatly. And this expression is my derivative. So I can use this to find the slope of any tangent line. One application of implicit differentiation is that it allows us to find derivatives of inverse functions. So here's a new rule for us. The derivative of arcsine is equal to 1 over 1 root 1 minus x squared. So why is that true? I'm going to use implicit differentiation to prove that this is the case. Remember that y is equal to arcsine of x if and only if, so this is like a definition, sine of y is equal to x and y is between these two angles. Okay, so I'm going to use this formulation here. I'm going to work from here, and I'm going to apply implicit differentiation to find the derivative of y with respect to x. So this gives me cosine of y times y prime is equal to 1. Now step 2 of implicit differentiation is I'm going to solve for y. So you get y prime is equal to 1 over cosine y. The only issue here is that I want my derivative to be in terms of x. So I need to find a way to express cosine y in terms of x. I'm going to use the Pythagorean identity, sine squared y plus cosine squared y is equal to 1. So I get cosine squared y is equal to 1 minus sine squared y. Solving for cosine y, I get plus or minus 1 minus sine squared y. One thing to notice is that y is between negative pi over 2 and pi over 2, so it's in either the first quadrant or the fourth quadrant, which means cosine is positive. So I can reduce to this case. I'm just going to rewrite that. The second thing to notice is that we said sine of y is equal to x, so using this, I'm going to rewrite cosine y as 1 minus x squared. Okay, so this allows me to rewrite this as 1 over root 1 minus x squared, and there I have my derivative of arcsine, and that's where this rule follows from. You could do something similar for the other trig functions. What I expect you to memorize is arcsine's derivative, cosine's derivative, and arctangent. Okay, so these you should know. And you could just look them up in the textbook. So let me just do one more example here. Let's suppose I want to find the derivative of arcsine of 3x squared minus 7e to the x. So here I have an inside function. I'm going to have to use the chain rule. And my outside function is our new function, arcsine. So the derivative in this case is going to be, well, I look at the derivative of the outside function, but I'm going to be inserting the inside function in here. So this is 3x squared minus 7e to the x. And then I'm going to be multiplying by the derivative of the inside function. So this is 6x minus 7e to the x. And you can clean this up a little bit, but this is our derivative.